Magnetic braking with Faraday. Introduction. The purpose of this law was to observe Faraday's law by dropping a magnet through a tube of aluminum foil. The results showed an experimental fall time of 1.24 seconds and a computational fall time of 1.16 seconds. For the system and surroundings, the system consisted of the magnet and the aluminum tube, while the surroundings included everything else. The lab. In the lab, we used a magnetometer app to find the north pole of the magnet. We set up the aluminum tube and dropped the magnet through the tube while timing how long it took to fall. This process was repeated 4 more times for a total of 5 trials. Some fundamental principles that were used were the Biot-Savart law, Faraday's law, magnetic flux, magnetic force, and Newton's second and third laws. These concepts govern the interaction between the magnetic field, the induced currents, and the forces acting on the magnet. The model and experiment made several key assumptions. Error resistance was considered negligible. Only gravity and the magnetic force were accounted for. The magnet acted as a magnetic dipole, and the aluminum tube was modeled as an ideal conductor. Observations and data. The tube's length was 0.3 meters and its radius was 0.03 meters, with an inner radius of 0.024 meters. The magnet's mass was 0.025 kilograms and the average fall time was 1.24 seconds. In the data table, you can see the results for each trial, with times ranging from 1.21 to 1.27 seconds. Part 2. 2 key questions were explored. First, why can't we use a Faraday's tube, like a steel pipe for example? The answer is that the magnet would stick to the sides of the tube and it wouldn't fall through. Second, how does the magnet fall through the tube compared to free space? The tube induces resistance against the magnet, slowing its fall compared to a free fall scenario. Computational model. This slide shows the computational model used to simulate the system. The Python code analyzed the induced currents and magnetic forces as the magnet fell through the tube. On the graph, you can see the velocity versus time plot, which demonstrates how the magnet's velocity changed over time. Computational model continued. The computational model accounted for the gravitational and magnetic forces on the magnet. The graph highlights the point where forces balance, resulting in the magnet reaching terminal velocity during the fall. Some possible errors that may be introduced are difficulty keeping track of the exact time it took for the magnet to fall. And also, the magnetic moment, or mu, used in the computational model was higher than the value measured in Lab 3, suggesting potential inaccuracies in earlier measurements. Discussion. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red corresponds to counterclockwise current as per Lenz's law, while blue indicates clockwise current. Flipping the magnet would reverse the direction of the induced current. Comparing the real-world system to the computational model, the total fall times were fairly close. However, the model could be improved by splitting the tube into more rings for greater accuracy. The velocity versus time plot shows that the forces on the magnet were unbalanced at the beginning, became balanced at terminal velocity, and became unbalanced again as it sped up at the end. Exploring hypothetical scenarios. If the resistivity of the conductor were nearly zero, the induced current would be much greater, causing a stronger magnetic force and slowing the magnet even more. If holes or slots were cut into the tube, the ring's current could be reduced and the magnet would fall faster. And in conclusion, this lab successfully demonstrated Faraday's law and the phenomenon of magnetic braking. By combining experimental and computational results, we gain insights into the dynamics of induced currents and their impact on the forces acting on the magnet. And thank you for listening to my presentation on Lab 5.